Okay, in this video we're going to talk about how to take derivatives of the logarithmic functions we've discussed in the past. The simplest one is the natural logarithm. So what's the derivative of the natural log of x? Well, to answer this question, I'm going to rephrase it slightly. That is, I'm going to call y equal to the natural log of x, and I want to know y prime. I want to know the derivative of y with respect to x. I'm going to use the inverse property of the natural logarithm, which says that the equation y equals the natural log of x is really the same as the equation e to the power y equals x. And then I'm going to take the derivative of that equation, both sides, with respect to x. To do that, I have to use implicit differentiation because I'm taking the derivative with respect to x of some y stuff. So what's the derivative of e to the y? Well, the derivative of e to a power is just that same thing, e to the power, but then I have to multiply by the derivative of the power. That's either implicit differentiation rule or the chain rule. You can think of it either way. But the derivative of e to the y is e to the y times the derivative of y. Then on the right-hand side of the equal sign, I just have to take the derivative of x, which is 1. If I divide through by e to the y, I get dy dx is 1 over e to the y. And that's 1 over x, because remember, e to the y is the same as x. That's how we started. So I found y prime. I found that y prime is 1 over x. That means the derivative of the natural log function is just 1 over x. So here's a slightly more complicated derivative. What's the derivative of the natural log of x? To the 4th power. Well, again, I get to remember the chain rule. The derivative of something to the 4th power is 4 times the something cubed. But then I have to multiply times the derivative of the something, the derivative of the inside part. But now I know that that's just 1 over x. The derivative of natural log of x is 1 over x. So I have 4 natural log of x cubed times 1 over x, and I can rewrite, maybe make it look a little bit nicer, as 4 times the natural log of x cubed all over x. Okay, a different example. Let's find the derivative of the natural log of the tangent of x. So again, this is a composition of functions. I have an outer and an inner function, so I need to use the chain rule. The derivative of the natural log of something on the previous slide we saw was 1 over the something. So the derivative of the natural log of tan x is 1 over tan x. But that's not all. You have to multiply times the derivative of that inside thing. So times the derivative of tan x. Everybody remember the derivative of tangent is secant squared. So I have secant squared x over tangent x. Now that's one way to write the answer. I just want to point something out. You could keep simplifying if you wanted. So take that secant squared x over tangent x, and remember that secant is 1 over cosine, and tangent is sine over cosine, so that's 1 over cosine x, quantity squared, over sine x over cosine x. Well, dividing by that fraction on the bottom is the same as multiplying times its reciprocal, and then I can cancel out a cosine, and so I have 1 over cosine x sine x. Both the cosine and sine are on the bottom. And 1 over cosine is secant, and 1 over sine is cosecant, so I can rewrite that as secant of x times cosecant of x. That's the same answer, it's just written in a very different way. I just did this to point out that, especially with trig functions, but even with other functions, the same expression, the same answer, can have 2 or more forms that look really, really different. Okay, so just because your answer doesn't look like the answer I write on the board when we're working in class doesn't mean it's necessarily wrong. You have to sort of see if trig identities or something can be used to turn one into the other. In the previous example, we did the derivative of the natural log of a thing. In that last example, it was the natural log of tangent x, but we can think of taking the derivative of the natural log of any old function, g of x. Well, how would we do that? The derivative of a natural log is 1 over the thing, so 1 over g of x, but then the chain rule says I have to multiply times the derivative of the inside, so that's times a g prime of x. So that is the derivative of a natural log of something is the derivative of the something over the original something. So the derivative of natural log of g is g prime over g, and you can use this to quickly do derivatives of natural log of stuff. I just want to remind you that everything you learned in Calculus 1 is still there. That is, we're talking about how to do derivatives, but what did we use derivatives for? Well, lots of things, and so you can use this stuff about derivatives of logs to answer questions about lots of different things, right? Rates of change. Derivatives tell you rates of change of something with respect to something else. They tell you the slope of a tangent line. They tell you whether a function is increasing or decreasing. Second derivatives tell you about concavity, concave up or concave down. You can get lots of information about what a graph looks like, the shape of a graph. You can find the maximum or minimum value of different functions, etc. So all that stuff is still stuff you need to remember. Okay, now what about integrals? The easiest integral, the kind that you sort of heaved a sigh of relief when it showed up, was taking the integral of just the variable to a power, so the antiderivative or integral of x to the n dx. And that was easy. You just add 1 to the power and then divide by that new power. So x to the n plus 1 over n plus 1, right? The integral of x squared is x cubed over 3. The integral of x to the 18th is x to the 19th over 19, and so on. But there was one big giant exception, and that is you can't divide by 0. So if n plus 1 is 0, there's a problem. So if n equals -1, this didn't work. That is, we had no idea how to do the integral of x to the -1 power. That's the same thing as 1 over x, right? X to the -1 is 1 over x. So we had no idea how to do the integral of 1 over x. But now we do. Why? Well, because what that means is give me a function whose derivative is 1 over x, right? That's what an integral is. That's what an antiderivative is. I'm looking for a function whose derivative is this thing, 1 over x. And we know a function whose derivative is 1 over x. The natural log of x is sort of the first thing you would think of, but its domain is only positive numbers. And in the book, they show why we can actually use the natural log of the absolute value of x. It has the same derivative, 1 over x. And its domain is all real numbers except for 0. So it's the same derivative, so it's another antiderivative, but it's got a bigger domain. So that's what we use. In other words, the function whose derivative is 1 over x, the most general function whose derivative is 1 over x, is the natural log of the absolute value of x, plus any constant. So the most general antiderivative, and the thing we will generally use when we write down antiderivatives, is the antiderivative of 1 over x, or the integral of 1 over x dx, is equal to the natural log of the absolute value of x plus a constant. That is something you should know backwards and forwards. And it can let us do some integrals that we had no idea how to do before. So we knew how to do the integral of sine or cosine, but the integral of tangent eluded us because we don't know an antiderivative of tangent of x. We have no idea of a function whose derivative would be tangent, right? The derivative of secant is secant tangent, but not just plain tangent. So we don't know any functions whose derivative is just tangent, and that's what we need to find. So let's do it. First, rewrite tangent as sine over cosine, and then I'm going to use u substitution. I let u equal the denominator cosine x. That makes du negative sine x dx. And notice that that sine x dx thing is showing up in our integral, sine of x times dx. So what I've got there is a u on the bottom and a negative du on top. So the integral turns into negative 1 over u du. Pull that negative outside the integral. And notice that that integral of 1 over u is exactly what we were just talking about, only the variable is now called u instead of x. So that integral is the natural log of the absolute value of u plus c. Only in this case there's an extra negative sign outside it. Now I can replace that u with what it equaled, which was cosine of x. And I can use a property of logs to point out that negative 1 times a natural log is the same as the natural log of the thing to the negative 1 power. Remember, this is one of the properties of logs, and they'll be coming up over and over again, so you need to get used to them. So that negative on the outside turns into a power of negative 1. Well, what does that mean? That means 1 over, so that's really the natural log of 1 over cosine x, absolute value, plus a constant, and 1 over cosine x is generally called secant x. So what we get is the natural log of the absolute value of secant x plus any constant. So we found it. We found an antiderivative of tangent x. The antiderivative of tangent x, or the integral of tangent x dx, is the natural log of the absolute value of secant x plus c. Ta-da! All right. So here's your video question. Check that answer. How do I know that I got the correct answer? You need to think about how do you check antiderivatives? How do you check integrals? And the answer is not to do an integral or an antiderivative. It's to do something else. Okay, so bring that to class and turn it in, and I will see you there.